Introduction to OpenID Connect. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. OpenID Connect, commonly abbreviated as OIDC, represents a modern authentication layer built on top of the OAuth 2.0 protocol framework. While OAuth 2.0 provides a robust mechanism for authorization, allowing applications to access resources on behalf of users, it was never designed to handle authentication directly. This is where OpenID Connect comes in, filling a critical gap in the identity and access management landscape. OpenID Connect extends OAuth 2.0 by adding an identity layer that enables clients to verify the identity of end users based on authentication performed by an authorization server, and to obtain basic profile information about the user in an interoperable and REST-like manner. The evolution of authentication protocols has been driven by the increasing complexity of modern web applications and the need for seamless single sign-on experiences across multiple services. Before OpenID Connect, developers often had to implement custom authentication solutions or rely on proprietary protocols that lacked standardization. This led to security vulnerabilities, inconsistent user experiences, and significant development overhead. OpenID Connect emerged as a standardized solution that leverages the proven OAuth 2.0 authorization framework while adding the authentication capabilities that applications need to verify user identities securely. What makes OpenID Connect particularly powerful is its use of JSON Web Tokens, or JWTs, to convey identity information. Unlike traditional session-based authentication where the server maintains state, JWTs are self-contained tokens that carry user identity claims within them. This design enables stateless authentication, which is essential for modern distributed applications and microservices architectures. The tokens are cryptographically signed, ensuring their integrity and authenticity, and can optionally be encrypted to protect sensitive information from unauthorized access. Core components and terminology. Understanding OpenID Connect requires familiarity with its fundamental components and the roles they play in the authentication flow. At the heart of the system is the OpenID provider, often abbreviated as OP. This is the authorization server that authenticates users and issues tokens. Major providers like Google, Microsoft Azure AD, Okta, and Auth0 act as OpenID providers, offering authentication services that applications can integrate with. The OpenID provider is responsible for managing user credentials, performing authentication, and generating the tokens that prove a user's identity. On the other side of the equation is the relying party, or RP, which is the application that wants to authenticate users. The relying party trusts the OpenID provider to authenticate users on its behalf and relies on the tokens issued by the provider to establish user sessions. This trust relationship is established through configuration, where the relying party registers with the OpenID provider and receives client credentials that it will use to communicate with the provider during the authentication process. The end user is the person who is trying to authenticate to access the application. From the user's perspective, OpenID Connect often manifests as the familiar sign in with Google or sign in with Microsoft buttons they see on websites. When they click these buttons, they are redirected to the OpenID provider's authentication page, where they enter their credentials. After successful authentication, they are redirected back to the application with tokens that prove their identity. Three types of tokens are central to OpenID Connect's operation. The ID token is a JWT that contains claims about the authentication event and the user. It is the primary mechanism through which the relying party learns about the user's identity. The access token, inherited from OAuth 2.0, allows the application to access protected resources on behalf of the user. Finally, the refresh token is a long-lived credential that can be used to obtain new access tokens when they expire, without requiring the user to authenticate again. The ID token structure. The ID token is the cornerstone of OpenID Connect, carrying essential information about the authenticated user in a standardized, verifiable format. As a JSON web token, it consists of three parts separated by periods: the header, the payload, and the signature. Each part is base64 URL encoded, creating a compact string that can be easily transmitted over HTTP. The structure is designed to be both human-readable when decoded and cryptographically secure when validated. The header section contains metadata about the token itself, specifically the algorithm used to sign it and the token type. Common signing algorithms include RS-256, which uses RSA with SHA-256, and ES-256, which uses elliptic curve digital signature algorithm with SHA-256. The choice of algorithm impacts both security strength and performance characteristics. The header also includes the key ID, or KID parameter, which helps the recipient identify which public key to use when verifying the token's signature, particularly important when the OpenID provider rotates keys regularly for security. The payload section is where the actual claims about the user and the authentication event reside. Claims are statements about an entity, typically the user, and include standard fields defined by the OpenID Connect specification. The issuer claim identifies the OpenID provider that issued the token. The subject claim contains a unique identifier for the user, which remains constant across sessions. The audience claim specifies which application the token is intended for, preventing token reuse across different applications. Temporal claims like issued at, expiration time, and not before define the token's validity period, typically ranging from 5 minutes to an hour. Additional claims provide context about the authentication event itself. The authentication time claim records when the user actually authenticated, which is crucial for applications that require recent authentication for sensitive operations. The nonce claim, when present, ties the token to the authentication request, preventing replay attacks. The authentication context class reference, or ACR claim, indicates the strength of the authentication method used, such as whether multi-factor authentication was employed. The authentication methods reference, or AMR claim, lists the specific authentication methods used, like password, one-time password, or biometric authentication. Authorization code flow. The authorization code flow is the most secure and widely recommended flow in OpenID Connect, particularly suitable for server-side web applications that can securely store client secrets. This flow provides strong security guarantees by never exposing tokens to the user's browser directly, instead using a temporary authorization code that is exchanged for tokens through a secure back-channel communication between the application server and the OpenID provider. The flow begins when a user attempts to access a protected resource in the application. The application redirects the user's browser to the OpenID provider's authorization endpoint, including several critical parameters in the URL. The response type parameter is set to code to indicate that an authorization code is requested. The client ID identifies the application to the OpenID provider. The redirect URI specifies where the OpenID provider should send the user after authentication, and this URI must exactly match one of the URIs registered with the provider during application setup. The scope parameter includes OpenID to indicate that OpenID Connect authentication is desired, along with other scopes like profile or email to request additional user information. The state parameter plays a crucial security role by preventing cross-site request forgery attacks. The application generates a random, unguessable value, stores it in the user's session, and includes it in the authorization request. When the OpenID provider redirects back to the application, it includes this state value, and the application verifies that it matches the stored value before proceeding. The nonce parameter serves a similar purpose but is specifically designed to prevent ID token replay attacks. It is included in the authorization request and must appear as a claim in the returned ID token, allowing the application to verify that the token was issued in response to its specific authentication request. At the OpenID provider, the user is presented with a login page where they enter their credentials. Depending on the provider's configuration and the authentication context, this might involve a password, multi-factor authentication, or other authentication mechanisms. After successful authentication, the provider may present a consent screen asking the user to approve the application's access to their information. This consent is a critical privacy protection, ensuring users understand what data they are sharing with applications. Once consent is granted, the OpenID provider redirects the user back to the application's redirect URI with an authorization code in the URL parameters. The application receives the authorization code and immediately performs several security validations. It verifies that the state parameter matches the value it stored at the beginning of the flow, confirming that this response corresponds to its original request and hasn't been tampered with. The application then makes a server-to-server post request to the token endpoint, trading the authorization code for tokens. This request includes the authorization code, the client ID and client secret for authentication, the grant type set to authorization code, and the redirect URI for verification. The token endpoint responds with an ID token, an access token, and typically a refresh token, all in JSON format. Implicit flow and hybrid flow. The implicit flow was originally designed for browser-based applications, particularly single-page applications that cannot securely store client secrets because all their code runs in the browser where users can inspect it. In this flow, tokens are returned directly in the URL fragment after authentication, without the intermediate authorization code exchange. The flow begins similarly to the authorization code flow, but with the response type set to ID token or just ID token depending on whether an access token is also needed. When using the implicit ID flow, the OpenID provider authenticates the user and immediately returns the requested tokens in the URL fragment of the redirect back to the application. URL fragments are the part of the URL after the hash symbol, and they are significant because they are not sent to the server in HTTP requests, only processed by browser-side JavaScript. This design attempts to prevent tokens from being logged on servers, though it does not protect against other attack vectors like malicious browser extensions or cross-site scripting vulnerabilities. However, the security community has increasingly recognized significant vulnerabilities in the implicit flow. Because tokens are exposed in the URL, they can be intercepted by malicious actors through browser history, referrer headers if the user navigates away, or various injection attacks. Additionally, without the authorization code exchange step, there is less opportunity to verify the authenticity of the authentication event. For these reasons, current best practices strongly recommend against using the implicit flow for new applications, instead favoring the authorization code flow with PKCE extension, which provides better security even for browser-based applications. The hybrid flow attempts to combine elements of both the authorization code flow and the implicit flow, providing flexibility for applications with both front-end and back-end components. In this flow, some tokens can be returned immediately in the front channel through the redirect, while others are retrieved through the back channel token endpoint exchange. For example, an application might request an ID token in the front channel for immediate user identification while retrieving the access token through the more secure back channel. The response type in a hybrid flow might be code ID token or code ID token, with each combination offering different trade-offs between immediate token availability and security. PKCE extension for enhanced security. Proof key for code exchange, universally referred to as PKCE, represents a critical security enhancement to the authorization code flow. It was originally developed to protect mobile applications, but is now recommended for all public clients, including single-page applications. PKCE addresses a fundamental vulnerability in the basic authorization code flow when used by applications that cannot securely authenticate with the OpenID provider. Specifically, it guards against authorization code interception attacks where malicious applications can steal authorization codes and exchange them for tokens. The PKCE mechanism introduces a dynamic client secret that changes with every authentication request, eliminating the need for a static client secret, which public clients cannot securely store. This dynamic secret is established through a challenge-response protocol using cryptographic techniques. At the start of the authentication flow, before redirecting the user to the OpenID provider, the application generates a random string called the code verifier. This verifier is a high-entropy cryptographic random string between 43 and 128 characters long, using unreserved characters from the URL specification, including uppercase and lowercase letters, digits, hyphens, periods, underscores, and tildes. From this code verifier, the application derives a code challenge using one of two transformation methods. The plain method simply uses the code verifier as the challenge without transformation, but this is only suitable when the communication channel is completely secure. The more secure and recommended method is S256, which means SHA-256 hashing. In this method, the application computes the SHA-256 hash of the code verifier. Then base 64 URL encodes the hash to create the code challenge. This one-way transformation means that even if an attacker intercepts the code challenge, they cannot reverse it to obtain the code verifier. When the application initiates the authorization request, it includes the code challenge and the challenge method in the authorization URL parameters, alongside the standard OpenID Connect parameters. The OpenID provider stores these values associated with the authorization code it generates. Later, when the application exchanges the authorization code for tokens at the token endpoint, it must include the original code verifier in the request. The OpenID provider then applies the same transformation method to the provided verifier and compares the result to the stored code challenge. Only if they match will the provider issue tokens, ensuring that only the application that initiated the authentication request can complete it. This mechanism effectively prevents authorization code interception attacks because an attacker who intercepts the authorization code does not have access to the code verifier, which was never transmitted to the OpenID provider in its original form. Even if an attacker compromises the application's redirect URI and intercepts the authorization code, they cannot exchange it for tokens without the code verifier, which remains secure in the legitimate application's memory. For these reasons, PKCE has become a mandatory requirement in OAuth 2.1 and is strongly recommended for all OpenID Connect implementations, regardless of application type. Token validation and security. Proper token validation is absolutely critical to OpenID Connect security. Simply receiving a token is not sufficient. The relying party must perform thorough validation to ensure the token is authentic, intended for this application, and still valid. Skipping or improperly implementing validation steps can lead to serious security vulnerabilities, including unauthorized access, token replay attacks, and identity spoofing. The OpenID Connect specification defines mandatory validation steps that must be performed every time a token is received. The first validation step is signature verification. ID tokens are signed using cryptographic algorithms, and the relying party must verify this signature using the public key of the OpenID provider. OpenID providers expose their public keys through a standardized endpoint called the JSON Web Key Set Endpoint, or JWKS endpoint, typically found at a well-known URL ending in /keys. This endpoint returns a JSON document containing one or more public keys, each identified by a key ID. The relying party retrieves these keys, caches them for performance, and uses the key matching the KID parameter in the token's header to verify the signature. This verification proves that the token was indeed issued by the claimed OpenID provider and has not been tampered with in transit. After signature verification, the relying party must validate the token's claims. The issuer claim must exactly match the OpenID provider's issuer identifier that the relying party is configured to trust. Even a small difference, like the presence or absence of a trailing slash, should cause validation to fail. The audience claim must contain the relying party's client ID, confirming that this token was issued for this specific application. If the AUD claim contains multiple values, the relying party must verify that its client ID is among them and that an AZP claim is present, indicating the authorized party. Temporal validation ensures the token is being used within its valid time window. The current time must be after the not before time if this claim is present, and before the expiration time. Relying parties typically add a small clock skew allowance, perhaps 30 to 60 seconds, to account for minor time synchronization differences between servers. However, this allowance should be minimal. ID tokens are meant to be short-lived, typically expiring within minutes or hours of issuance. If a nonce was included in the authentication request, the relying party must verify that the nonce claim in the ID token matches the value it generated and stored for this authentication attempt. This validation prevents token replay attacks where an attacker might try to reuse a token from a previous authentication session. Similarly, if the @hash claim is present, which is mandatory when an access token is issued alongside the ID token in the same response, the relying party should validate it by hashing the access token and verifying it matches the @hash value, confirming that the access token and ID token were issued together. UserInfo endpoint and claims. While the ID token contains essential authentication information and basic identity claims, many applications need additional user profile information to personalize the user experience or make authorization decisions. The UserInfo endpoint serves this purpose, providing a standardized way to retrieve comprehensive user profile information from the OpenID provider. This endpoint is accessed using the access token obtained during authentication, and it returns user claims in JSON format, ensuring interoperability across different OpenID provider implementations. The UserInfo endpoint is particularly useful when applications need more detailed user information than what fits comfortably in an ID token. While ID tokens should be kept relatively small for performance reasons, since they are transmitted frequently and need to be validated each time, the UserInfo endpoint can return extensive profile information without these constraints. Common claims available from the UserInfo endpoint include the user's full name, given name, family name, middle name, nickname, preferred username, profile page URL, picture URL, website, email address, email verification status, gender, birth date, time zone, locale for language preferences, phone number verification status, and formatted postal address. To access the UserInfo endpoint, the relying party makes an HTTP GET or POST request to the endpoint URL, including the access token in the authorization header using the bearer token scheme. The OpenID provider validates the access token, checking its signature, expiration, and that it was issued with the appropriate scopes to access user information. If the token is valid, the provider returns a JSON response containing the requested claims. The set of claims returned depends on the scopes that were requested during authentication and that the user consented to share. The relationship between scopes and claims is fundamental to OpenID Connect's privacy model. The OpenID scope is mandatory and simply enables OpenID Connect functionality, allowing the issuance of an ID token. The profile scope requests access to default profile claims like name, family name, given name, middle name, nickname, preferred username, profile, picture, website, gender, birth date, zone info, and locale. The email scope requests the email address and email verified claims. The address scope requests the address claim containing a formatted address. The phone scope requests phone number and phone number verified claims. Applications request only the scopes they actually need, following the principle of least privilege and respecting user privacy. Discovery and dynamic configuration. OpenID Connect Discovery defines a standardized mechanism for relying parties to automatically discover information about an OpenID provider's configuration, eliminating the need for manual configuration and reducing integration complexity. This discovery mechanism is built around the concept of the OpenID Provider Configuration Document, a JSON document hosted at a well-known URL that contains all the metadata a relying party needs to interact with the provider. This standardization enables tools and libraries to automatically configure themselves when given just the provider's base URL. The discovery process begins with the OpenID provider's issuer ID, which is a URL that uniquely identifies the provider. To discover the provider's configuration, the relying party constructs a well-known URL by appending the path /.wellknown/OpenID configuration to the issuer ID. For example, if the issuer is https://accounts.example.com, the configuration document would be found at https://accounts.example.com/.wellknown/OpenID configuration. This standardized path makes discovery predictable and automatable across all OpenID Connect providers. The configuration document contains essential endpoints that the relying party needs to interact with the OpenID provider. The authorization endpoint URL is where authentication requests are initiated. The token endpoint URL is where authorization codes are exchanged for tokens. The UserInfo endpoint URL is where user profile information is retrieved. The JWKS URI points to the JSON web key set containing the provider's public keys for token signature verification. The registration endpoint URL, if present, allows for dynamic client registration. End session endpoint URL enables logout functionality, allowing applications to terminate user sessions at the provider. Beyond endpoints, the configuration document declares the provider's capabilities and supported features. The supported response types list indicates which OAuth 2.0 and OpenID Connect flows are available, such as code for authorization code flow, ID token for implicit flow, or code ID token for hybrid flow. The supported grant types include authorization code, implicit, refresh token, and potentially others, for example, client credentials or device code. The supported scopes list shows which scopes are available for requesting user information. The token endpoint authentication methods supported indicate how clients can authenticate when calling the token endpoint, typically including client secret basic, client secret post, or private key JWT for higher security. Additional configuration details include the supported claims that can be returned in ID tokens and from the UserInfo endpoint. The supported signing algorithms for ID tokens, UserInfo responses, and request objects enable clients to verify they can work with the provider's cryptographic requirements. The subject types supported indicate whether the provider uses public subject identifiers that are consistent across all clients, or pairwise identifiers that are unique per client to enhance privacy. This rich metadata enables relying parties to automatically adapt their behavior based on provider capabilities, making integration more flexible and maintainable. Session management and logout. Session management in OpenID Connect extends beyond the initial authentication to encompass the user's entire session lifecycle. This includes monitoring the session state, handling session timeouts, and properly terminating sessions during logout. Unlike traditional server-side session management, where the application maintains session state, OpenID Connect introduces complexities. This is because sessions may exist at multiple layers: at the OpenID provider, at the relying party application, and potentially at other applications sharing the same single sign-on session. The session management specification in OpenID Connect defines mechanisms for relying parties to monitor the user's login status at the OpenID provider. This is particularly important in single sign-on scenarios where users might have sessions with multiple applications. If a user logs out of one application or their session expires at the OpenID provider, other applications need a way to detect this change and respond appropriately, typically by requiring re-authentication or clearing their local session state. One approach to session monitoring uses the check session iframe technique, where the relying party includes a hidden iframe pointing to the OpenID provider's checked session endpoint. The relying party's JavaScript code periodically posts messages to this iframe using the HTML5 post message API, passing the session state value that was received during authentication. The iframe responds indicating whether the session state has changed. If a change is detected, the relying party can initiate a silent re-authentication attempt in a hidden iframe to refresh the session, or it can prompt the user to re-authenticate if that fails. Front channel logout enables the OpenID provider to notify relying parties when a user logs out from the provider. When a user initiates logout from the OpenID provider, the provider returns an HTML page containing hidden iframes that point to the registered front channel logout URLs of all relying parties where the user has active sessions. The browser loads these iframes, triggering the relying parties to clear their local session state. This mechanism allows for coordinated logout across multiple applications, though it has limitations in terms of reliability and privacy since it depends on browser behavior and cross-site iframe functionality. Back-channel logout provides a more reliable alternative by using direct server-to-server communication. When a user logs out, the OpenID provider makes HTTP POST requests to the registered back-channel logout endpoints of all affected relying parties, including a logout token in the request. This logout token is a JWT containing claims identifying the user and the logout event. Relying parties validate the logout token and terminate the user's session. This approach is more reliable than front-channel logout because it does not depend on browser behavior, and it works even if the user's browser is closed or offline. However, it requires relying parties to expose a publicly accessible endpoint that the OpenID provider can call. Client registration and metadata. Before a relying party can begin using OpenID Connect to authenticate users, it must first register with the OpenID provider. This registration process establishes the trust relationship between the application and the provider, and it configures essential parameters that govern how they will interact. Client registration can be performed manually through the provider's administrative interface, or dynamically through the Dynamic Client Registration Protocol, which is a standardized API for programmatic registration. During registration, the relying party provides metadata that describes its characteristics and requirements. The most critical piece of information is the redirect URI, which specifies where the OpenID provider should send the user after authentication. This URI must be registered exactly, including the protocol, domain, port, and path. The OpenID provider will only redirect to URIs that match the registered values precisely, preventing attackers from hijacking the authentication flow by substituting their own redirect URI for added security. Organizations should use HTTPS for all redirect URIs and avoid using wildcards or overly permissive patterns. The client type designation determines how the client will authenticate with the OpenID provider. Confidential clients are applications that can securely store credentials, such as server-side web applications running on protected infrastructure. These clients are issued a client secret, which they must present when exchanging authorization codes for tokens. Public clients, on the other hand, cannot securely store secrets because their code runs in environments that users can inspect, such as single-page applications in browsers or native mobile applications. Public clients rely on other security mechanisms like PKCE to protect against attacks, and they are not issued client secrets or are issued secrets that are not used for authentication. Additional client metadata includes the application type, which can be web for traditional web applications or native for mobile and desktop applications. The grant types specify which OAuth 2.0 flows the client is authorized to use, such as authorization code, implicit, or refresh token grants. The response types indicate which types of responses the client can request from the authorization endpoint, such as code for authorization codes, ID token for ID tokens, or combinations for hybrid flows. Token endpoint authentication method specifies how the client will authenticate when calling the token endpoint, with options including client secret basic, client secret post, private key JWT, or none for public clients. Client metadata also includes human-readable information for display purposes. The client name is shown to users during the consent process, helping them understand which application is requesting access. The logo URI points to an image representing the application, enhancing user recognition and trust. The client URI links to the application's homepage or terms of service. Policy URIs and terms of service URIs provide users with information about how their data will be used. Contacts specify email addresses for technical or administrative communication about the client. All this metadata helps users make informed decisions about granting consent and helps OpenID providers manage their registered clients effectively. Refresh tokens and token rotation. Access tokens in OpenID Connect are designed to be short-lived, typically expiring within minutes to hours of issuance. This limited lifetime reduces the window of opportunity for attackers who might compromise a token, but it creates a challenge for applications that need to maintain long-term access to resources without constantly prompting users to re-authenticate. Refresh tokens solve this problem by providing a long-lived credential that can be used to obtain new access tokens when the current ones expire, all without user interaction. When an application receives tokens from the token endpoint, it typically receives an access token, an ID token, and optionally a refresh token. The refresh token is a special credential that the application stores securely and uses exclusively with the token endpoint. When the current access token expires or is about to expire, the application makes a request to the token endpoint with the grant type set to refresh token, providing the refresh token as proof of its authorization. The OpenID provider validates the refresh token and, if it is still valid, issues a new access token. Depending on the provider's policy, it might also issue a new ID token and potentially a new refresh token. Refresh token rotation is a security practice where the OpenID provider issues a new refresh token each time the old one is used to obtain new access tokens. The old refresh token is immediately invalidated, meaning it can only be used once. This mechanism, called one-time use refresh tokens, provides important security benefits. If a refresh token is stolen and used by an attacker, the legitimate application's next attempt to use its refresh token will fail, alerting the application to the compromise. Similarly, if the legitimate application uses the refresh token first, the attacker's subsequent attempt will fail, alerting the OpenID provider to suspicious activity. When implementing refresh token rotation, applications must carefully handle the receipt of new refresh tokens. Each time the application successfully refreshes tokens, it must replace the stored refresh token with the new one provided in the response. Failure to do this will cause subsequent refresh attempts to fail because the old token has been invalidated. Applications should also implement proper error handling for refresh token expiration or revocation. If a refresh attempt fails, the application should clear its stored tokens and redirect the user to authenticate again, rather than repeatedly attempting to use an invalid refresh token. Refresh token lifetime and policy vary significantly across OpenID providers, and can often be configured per client. Some providers issue refresh tokens that never expire, while others limit them to days, weeks, or months. Some providers implement sliding expiration, where the refresh token's expiration is extended each time it is successfully used, maintaining the session as long as the user remains active. Others use absolute expiration, where the refresh token expires at a fixed time regardless of usage. Applications should be prepared to handle refresh token expiration gracefully and should never assume refresh tokens will last indefinitely. Providers can also revoke refresh tokens at any time due to security concerns, policy changes, or explicit user action like changing passwords or revoking application access. Security best practices and threat model. Implementing OpenID Connect securely requires understanding the threat model and applying comprehensive security controls throughout the authentication flow. The OAuth 2.0 threat model and security considerations document, along with OAuth 2.0 security best current practice, provide detailed analysis of potential attacks and mitigations. These threats range from credential theft and token interception to more sophisticated attacks like session fixation and authorization code injection. Authorization code interception attacks occur when an attacker intercepts the authorization code during the redirect from the OpenID provider back to the application. This can happen through various means, including network interception, malicious applications on the same device, or browser-based attacks. PKCE, which we discussed earlier, is the primary defense against this attack, making the intercepted code useless without the corresponding code verifier. All applications, not just public clients, should implement PKCE to defend against this threat. Additionally, authorization codes should have very short lifetimes, typically just a few minutes, and should be invalidated immediately after use. Redirect URI manipulation attacks attempt to send the authorization code or tokens to an attacker-controlled endpoint instead of the legitimate application. Attackers might try open redirects, subdomain takeovers, or parameter manipulation to achieve this. The primary defense is strict validation of redirect URIs at the OpenID provider. Providers must perform exact string matching of redirect URIs, not allowing pattern matching or wildcards unless absolutely necessary. Applications should use HTTPS for all redirect URIs to prevent network-level interception. The state parameter provides additional protection by binding the authentication request to the response, preventing attackers from substituting their own responses. Cross-site request forgery attacks against the redirect URI can trick users into completing an authentication flow initiated by an attacker, potentially linking the victim's account to the attacker's identity or causing other malicious outcomes. The state parameter is specifically designed to prevent this attack. The application generates a random, unguessable state value at the beginning of the authentication flow, stores it in the user's session, and includes it in the authorization request. When the OpenID provider redirects back, the application verifies that the state parameter in the response matches the stored value. If they don't match, the response is rejected as potentially malicious. Token theft can occur through various vectors including cross-site scripting attacks, browser history, logs, or compromised storage. Defense in depth is essential. Store tokens securely, preferably in HTTP-only cookies that JavaScript cannot access, or in secure storage mechanisms provided by the platform for native applications. Never log tokens or include them in URLs except where absolutely required by the protocol. Implement content security policies to mitigate XSS risks. Use short-lived access tokens to minimize the impact if they are stolen. Implement token binding or proof of possession mechanisms where available to tie tokens to specific clients or TLS sessions, making stolen tokens less useful to attackers. Request objects and JAR. Request objects represent an advanced feature of OpenID Connect that addresses security and privacy concerns associated with passing authentication parameters in URL query strings. When using the standard authorization endpoint, all request parameters, including scopes, redirect URIs, and state values, are visible in the URL. This creates several problems. URLs are logged by browsers, proxies, and servers. They appear in referrer headers, and they have length limitations that can be problematic for complex requests. Request objects solve these issues by packaging the authentication request parameters into a signed and optionally encrypted JSON web token. The JWT Secured Authorization Request Specification, often abbreviated as JAR, defines how to use request objects. Instead of passing individual parameters in the URL, the relying party creates a JWT containing all the request parameters as claims. This JWT is signed with the client's private key, proving that the request came from the legitimate client and hasn't been tampered with. The relying party can either pass this JWT directly in the request parameter of the authorization URL, or it can host the JWT on a web server and pass a request URI that points to it, allowing the OpenID provider to retrieve the request object. Creating a request object involves constructing a JWT with specific claims that mirror the standard authorization request parameters. The claims include response type, client ID, redirect URI, scope, state, and nonce, along with any additional parameters the authentication requires. The JWT header specifies the signing algorithm, typically RS-256 or ES-256, and identifies the key used for signing. The entire JWT is then included in the authorization request either directly as the request parameter, or by reference using the request URI parameter. When the OpenID provider receives an authorization request with a request parameter or request URI, it processes the request object before proceeding with authentication. If a request URI is provided, the provider fetches the JWT from that URL. The provider then validates the JWT signature to ensure the request came from the registered client and has not been tampered with. It extracts the claims from the JWT and uses them as the request parameters. Parameters passed both in the URL and in the request object must match exactly, or the provider should reject the request. This dual representation exists for backward compatibility, but the request object values take precedence. Request objects can also be encrypted, providing confidentiality for sensitive request parameters. This is particularly useful when the request contains personally identifiable information, such as ID token hints that might contain user identifiers, or when passing through environments where URL logging might create privacy concerns. Encrypted request objects use JSON web encryption, or JWE, wrapping the signed JWT in an encryption layer using the OpenID provider's public key. Only the provider can decrypt the request object, ensuring that even if the URL is logged or intercepted, the sensitive parameters remain confidential. Claims and Scopes Deep Dive. Claims in OpenID Connect are pieces of information asserted about an entity, typically the user. They represent the fundamental mechanism for conveying identity information from the OpenID provider to the relying party. Claims are returned either in the ID token or from the UserInfo endpoint, and they form the basis for making authorization decisions, personalizing user experiences, and fulfilling application requirements. Understanding the full breadth of available claims and how to request them effectively is essential for building robust OpenID Connect integrations. Standard claims defined by the OpenID Connect specification cover a comprehensive set of user attributes. The subject claim, abbreviated as SUB, uniquely identifies the user at the OpenID provider. This identifier is stable and never changes for a given user, making it suitable as a primary key for the user in the application's database. The name claim provides the user's full name in displayable form, while given name, middle name, and family name break down the name into components. The nickname claim offers an informal name, and preferred username suggests a username for the application to use, though it might not be unique across all users. Profile-related claims enable rich user experiences. The profile claim contains a URL pointing to the user's profile page at the OpenID provider. The picture claim provides a URL to an avatar or profile picture, which applications can display in the user interface. The website claim links to the user's personal website or blog. These claims help applications present familiar identity information to users, creating continuity between the OpenID provider's representation of the user and how they appear in the application. Contact information claims are essential for communication and verification. The email claim includes the user's email address. The email verified claim is a Boolean, indicating whether the provider has confirmed that the user controls this email address. Similarly, phone number and phone number verified claims provide telephone contact information and verification status. The address claim contains a structured JSON object with components including formatted address, street address, locality or city, region or state, postal code, and country. Applications should request only the contact information they actually need, respecting user privacy. Demographic and localization claims help applications tailor experiences. The gender claim indicates the user's gender, though applications should not make assumptions about which values might be present, as providers may support diverse representations. The birth date claim contains the user's date of birth in ISO 8601 format, useful for age verification or personalization. The zone info claim specifies the user's time zone in IANA time zone database format, enabling proper display of times and scheduling. The locale claim indicates the user's preferred language and region using BCP47 language tags, guiding interface localization. Custom claims extend beyond the standard set to address application-specific needs. OpenID providers can define custom claims for any information they maintain about users. Enterprise providers might include claims for employee ID, department, manager, cost center, or security clearance level. Social providers might include follower counts, verification badges, or account creation dates. When working with custom claims, applications should namespace them to avoid conflicts, typically using domain-based naming like https://example.com/claims/department. Applications request custom claims through custom scope definitions or using the claims parameter to request specific claims directly. Multi-factor authentication and step-up authentication. Multi-factor authentication, commonly abbreviated as MFA, significantly enhances security by requiring users to provide multiple forms of verification before granting access. In OpenID Connect, MFA integration is achieved through standardized mechanisms that allow relying parties to request or require additional authentication factors, and for OpenID providers to communicate what authentication methods were used. This enables applications to enforce security policies that require stronger authentication for sensitive operations without implementing the MFA mechanisms themselves. The Authentication Context Class Reference, known as ACR, provides a way for relying parties to request specific authentication strength levels. ACR values are URIs that represent different authentication policies or assurance levels defined by the OpenID provider. For example, an ACR value might represent password-only authentication, password plus email verification, password plus SMS verification, or password plus hardware token. Relying parties include the ACR values parameter in their authorization requests to indicate which authentication levels they are willing to accept. The OpenID provider authenticates the user according to one of these levels and returns the ACR claim in the ID token to indicate which level was actually achieved. The Authentication Methods Reference, abbreviated as AMR, provides granular information about the specific authentication methods that were used during the authentication event. While ACR represents an overall policy or assurance level, AMR lists the individual factors. Common AMR values include PWD for password authentication, OTP for one-time passwords, SMS for SMS verification codes, HWK for hardware cryptographic keys, MFA to indicate that multiple factors were used, and BIO for biometric authentication. The AMR claim contains an array of values, allowing the provider to specify all methods used. For instance, if a user authenticated with both a password and a hardware token, the AMR might contain both PWD and HWK. Step-up authentication enables applications to request additional authentication for sensitive operations even when the user already has an active session. For example, a banking application might allow users to browse their account with basic authentication, but require additional verification before initiating a wire transfer. Step-up authentication is implemented using the max_age parameter in the authorization request. This parameter specifies the maximum acceptable elapsed time since the user last actively authenticated, measured in seconds. If the current time minus the auth_time claim in the user's existing session exceeds the max_age value, the OpenID provider must authenticate the user again. Prompt parameters provide fine-grained control over the user experience of the authentication flow. The prompt parameter can take several values that modify how the OpenID provider interacts with the user. The value none instructs the provider not to display any authentication or consent user interfaces. If the user is not already authenticated, or if consent has not been previously granted, the provider returns an error. This is useful for checking authentication status without interrupting the user. The value login forces the provider to present the authentication interface even if the user has an active session, ensuring fresh authentication. The value consent requires the provider to prompt for consent even if it was previously granted. Multiple prompt values can be combined, and select account instructs the provider to prompt the user to select an account when multiple accounts exist. Implementing strong authentication policies requires careful consideration of both security and user experience. Applications should apply risk-based authentication, requiring stronger factors only when risk factors like unusual login location, device, or sensitive operation warrant additional verification. Federation and identity brokering. In enterprise environments and complex identity ecosystems, organizations often need to federate identity across multiple systems or broker authentication through intermediary identity providers. OpenID Connect serves as an excellent protocol for building these federated identity architectures, enabling single sign-on across organizational boundaries while maintaining security and giving users control over their identity information. Identity federation allows users to use credentials from one organization to access resources in another, while identity brokering positions an intermediate provider that translates between different protocols or federates multiple identity sources. Identity brokering involves an OpenID provider that does not maintain its own user credentials, but instead delegates authentication to one or more upstream identity providers. When a user attempts to authenticate, the broker presents options for which identity provider to use, or it might automatically select one based on the user's email domain or other identifying information. The broker then initiates an authentication request to the selected upstream provider, receives tokens from that provider, validates them, and issues its own tokens to the relying party. This architecture provides several benefits. It abstracts the complexity of multiple identity providers from applications, allowing centralized policy enforcement and audit logging. It enables protocol translation when upstream providers do not support OpenID Connect, and provides a consistent token format and claim structure regardless of the upstream provider. When implementing identity brokering, the broker must make critical decisions about claim mapping and transformation. Different identity providers use different claim names and formats for similar information. The broker normalizes these differences, mapping claims from upstream providers to a standard schema that relying parties expect. For example, one upstream provider might use email as a claim name while another uses mail or email_address. The broker maps all of these to a consistent claim name in its issued tokens. Similarly, the broker might enrich claims by combining information from the upstream ID token and UserInfo endpoint, or by adding claims from additional data sources like LDAP directories or HR systems. Subject identifier handling is particularly important in brokered scenarios. The subclaim uniquely identifies the user, and it must remain stable for a given user even when authenticating through different upstream providers. The broker typically implements one of several strategies. It might generate a new, broker-specific subject identifier that it maps to the upstream provider's subject identifiers in a database, ensuring consistency even if the user authenticates through different providers at different times. Alternatively, it might use the user's email address or username as the basis for the subject identifier, assuming these are unique and stable across providers. Pairwise subject identifiers provide another option, where the broker generates different subject values for different relying parties, enhancing privacy by preventing user tracking across applications. Token chaining and upstream token propagation create additional complexity. Should the broker pass along the original upstream access token to relying parties, or should it issue its own access tokens? Passing through upstream tokens maintains end-to-end trust and can enable direct API calls from relying parties to the upstream provider's resources. However, it exposes implementation details and creates tight coupling. Issuing broker tokens provides better abstraction and allows the broker to implement its own authorization policies, but requires the broker to act as an API gateway if relying parties need to access upstream resources. Mobile and native application considerations. Mobile and native applications present unique challenges and opportunities for OpenID Connect implementation. Unlike web applications that run in browsers with standardized security models, native applications run directly on devices with varying operating system capabilities, making security considerations more complex. The OAuth 2.0 for native apps specification, also known as RFC 8252, provides comprehensive guidance for implementing OpenID Connect in mobile and desktop applications, and these best practices have evolved significantly as mobile platforms have matured. The first critical decision for native applications is how to handle the authorization flow redirect. Early implementations often used embedded web views, where the application would display the OpenID provider's authentication page within a web view component controlled by the application. However, this approach has serious security and usability problems. Users cannot verify the authenticity of the authentication page, making phishing attacks trivial. The application can potentially access user credentials as they are entered. Sessions are not shared with the system browser, breaking single sign-on. For these reasons, embedded web views are strongly discouraged for OpenID Connect authentication. The recommended approach uses the system browser or an in-app browser tab, such as AS Web Authentication Session on iOS, custom tabs on Android, or similar platform-specific mechanisms. These technologies provide several advantages. They display the OpenID provider's authentication page in a secure environment that the application cannot tamper with or observe. Users can see the actual domain in the browser address bar, enabling them to verify they are entering credentials into the legitimate provider. The authentication state is shared with the system browser, enabling single sign-on across applications. When users have already authenticated with the provider in their browser, they can reuse that session without entering credentials again. Redirect URI handling for native applications requires special URL schemes or universal links. Traditional web redirect URIs don't work well for native applications because the application needs to be invoked when the OpenID provider completes the redirect. Custom URL schemes, such as COM, example.app://OAuth callback, allow the operating system to redirect back to the application. However, custom URL schemes have security limitations. On some platforms, multiple applications can register the same custom scheme, creating opportunities for authorization code interception. Universal links on iOS and app links on Android provide a more secure alternative, using HTTPS URLs that the operating system verifies are associated with the application through digital signatures or server-hosted configuration files. PKCE is absolutely mandatory for native applications. Because native applications are public clients that cannot securely store client secrets, PKCE provides the primary protection against authorization code interception. An attacker who manages to intercept the authorization code, either through a malicious application registering the same custom URL scheme or through operating system vulnerabilities, cannot exchange it for tokens without the code verifier. Native applications should always use the S256 challenge method with PKCE, generating high-entropy code verifiers of at least 43 characters. Token storage on mobile devices requires platform-specific secure storage mechanisms. Applications should never store tokens in shared preferences, user defaults, or other unencrypted storage locations. On iOS, the keychain provides secure, encrypted storage for tokens with options for additional protection using device biometrics or passcodes. On Android, the KeyStore system offers similar capabilities, allowing applications to store tokens encrypted with keys that cannot be extracted from the device. Refresh tokens, which are long-lived credentials, deserve special protection. Applications should store them with the strongest available security options, requiring device authentication to access them when possible. Access tokens, being shorter-lived, might use slightly less stringent storage depending on the application's security requirements, but should still be encrypted. Enterprise integration patterns. Enterprise adoption of OpenID Connect involves integrating with existing identity infrastructure, meeting complex compliance requirements, and serving diverse application portfolios that range from legacy systems to modern cloud-native applications. Enterprise implementations often involve identity providers like Azure Active Directory, Okta, Ping Identity, ForgeRock, or on-premises solutions like Active Directory Federation Services. These implementations must balance security, usability, and operational complexity while supporting thousands of users and hundreds of applications. Legacy application integration presents particular challenges when those applications weren't designed with modern authentication protocols in mind. These applications might expect authentication through LDAP, Kerberos, SAML, or proprietary mechanisms. Several patterns enable OpenID Connect integration with legacy systems. Reverse proxy authentication places a proxy server in front of the legacy application that handles OpenID Connect authentication and then forwards requests to the application with traditional authentication headers like HTTP Basic or Kerberos tickets. The legacy application sees only the traditional authentication it expects, while users benefit from modern single sign-on. Application gateways provide a similar function but with more sophisticated capabilities including session management, authorization enforcement, and API transformation. Protocol bridging enables interoperability between OpenID Connect and other identity protocols prevalent in enterprises. Many enterprise identity providers support both OpenID Connect and SAML 2.0. allowing different applications to use whichever protocol they are designed for while sharing a common user authentication. When an enterprise identity provider receives an OpenID Connect authentication request, it authenticates the user and issues OpenID Connect tokens. When it receives a SAML authentication request from a different application for the same user, it can reuse the same authentication session and issue a SAML assertion instead. This approach maintains single sign-on across the entire application portfolio regardless of which protocols individual applications support. Just-in-time provisioning addresses the challenge of synchronizing user accounts between identity providers and applications. Traditionally, enterprises use identity provisioning systems that batch synchronize user accounts from authoritative sources, like HR systems, to all applications, creating accounts before users first sign in. Just-in-time provisioning takes a different approach where user accounts are created in applications automatically when users first authenticate through OpenID Connect. The application examines the claims in the ID token or UserInfo response and creates a local user account with appropriate attributes. Subsequent authentications update the account with any changed information. This approach reduces provisioning overhead and ensures users have accounts only in applications they actually use, but it requires applications to handle account creation logic and decide how to map identity provider claims to local user attributes. Group and role mapping enables OpenID Connect to convey authorization information alongside authentication. While OpenID Connect primarily handles authentication, applications need to make authorization decisions about what authenticated users can do. Enterprises typically maintain group membership and role assignments in their identity providers, such as Active Directory groups, and these need to flow to applications. OpenID providers can include group memberships or role assignments as claims in ID tokens or UserInfo responses, typically using custom claims like groups or roles containing arrays of values. Applications consume these claims to make authorization decisions or to populate their own role-based access control systems. For scalability with users who have many group memberships, providers might include only a hash or reference in tokens and require applications to call additional APIs to retrieve full group lists. Audit logging and compliance reporting require capturing detailed information about authentication events, token issuance, and API access. Enterprise identity providers typically maintain comprehensive audit logs that record every authentication attempt, whether successful or failed, along with contextual information like IP addresses, device types, geographic locations, and authentication methods used. These logs support security operations, fraud detection, and compliance audits. OpenID Connect facilitates this by including relevant information in tokens through claims like auth time, AMR, and ACR that applications can log. Applications should also emit their own audit events when consuming tokens, creating a complete audit trail from initial authentication through application access. Regulatory requirements like GDPR, HEPA, or PCI DSS often mandate specific audit capabilities, and enterprise implementations must ensure OpenID Connect integrations satisfy these requirements. Future of OpenID Connect. In conclusion, OpenID Connect continues to evolve to address emerging security threats, new use cases, and lessons learned from widespread deployment. The OpenID Foundation maintains active working groups that develop extensions and profiles for specific scenarios. Several important specifications are in various stages of development and adoption, each addressing specific needs that have emerged as OpenID Connect has matured in production environments across thousands of organizations. Financial Grade API, abbreviated FAPI, represents a set of security profiles for OpenID Connect designed for high-security applications like banking and financial services. FAPI mandates strong security controls including requiring signed request objects, mandating PKCE, requiring sender-constrained tokens through mechanisms like mutual TLS or DPoP, and enforcing stricter validation requirements. Many regulatory frameworks for open banking around the world reference FAPI as the required security standard, making it increasingly relevant beyond just financial services. Any application handling sensitive data or high-value transactions can benefit from FAPI's rigorous security requirements. Continuous Access Evaluation Protocol, known as CAEP, addresses the limitation that traditional tokens remain valid until they expire, even if the user's situation changes. If an administrator disables a user's account, revokes their access to an application, or if suspicious activity is detected, applications currently using that user's tokens might continue to accept them until expiration. CAEP enables identity providers to push security events to relying parties in real time, notifying them when tokens should be revoked. Relying parties can then immediately terminate sessions or revoke access without waiting for tokens to expire naturally. This significantly reduces the window of vulnerability when credentials are compromised or when access rights change. Shared Signals and Events Framework generalizes the event notification mechanism pioneered in CAEP, enabling identity providers and relying parties to share a wide variety of security-relevant events beyond just token revocation. These might include suspicious login attempts, password changes, device compromise indicators, or compliance violations. Applications that receive these signals can adapt their behavior dynamically, requiring step-up authentication when risk increases, blocking access from compromised devices, or alerting security operations centers. This framework enables a more responsive and adaptive security posture across federated environments. Decentralized identity and self-sovereign identity represent a paradigm shift, where users control their own identity credentials through cryptographic keys and blockchain or distributed ledger technologies, rather than relying on centralized identity providers. While OpenID Connect is inherently centralized, with identity providers acting as trusted third parties, work is underway to bridge these models. Users might present verifiable credentials based on decentralized identifiers, which OpenID providers verify and then issue traditional OpenID Connect tokens for. This hybrid approach combines the privacy and user control benefits of decentralized identity with the proven interoperability and wide adoption of OpenID Connect. As we conclude this presentation, it is important to recognize that OpenID Connect has fundamentally changed how authentication works on the Internet. It has enabled the widespread adoption of single sign-on, improved security through standardization and best practices, enhanced user privacy by reducing password proliferation, and created an interoperable ecosystem where applications and identity providers from different vendors work together seamlessly. Whether you are building a simple web application that needs user authentication, implementing enterprise single sign-on across thousands of applications, or designing mobile applications with sophisticated security requirements, OpenID Connect provides a solid foundation with proven security characteristics and broad industry support. Thank you for your attendance. Please consider subscribing to the channel.